Okay, so welcome back everyone. We can start again. So today we are gonna finish the third chapter and also the second part on linear models, and we will start with the third part on nonlinear models and chapter 4 as well. So first, I'm just gonna remind you what we did during the last lecture. So the beginning of chapter 3, and we will then finish it. So in chapter 3, we discussed how to do inference on the beta coefficient in a linear model. So on the slope, on the causal effect when you assume that the model is causal. And we discussed how we usually do that with OLS, and why it's more complicated when you have high-dimensional data and you want to use lasso. And we discussed also some fixes, like some solutions to the problem with the lasso. So this was the basic problem. So if you recall, let's say we want to know what is the causal effect of education on earnings. And we assume that this is a causal model. So meaning the earnings is linear in education and experience, and there is some error term epsilon I, which is not correlated with the other variable. So you have exogeneity and linearity. As we say, to interpret this as a causal model, you need the causal model to follow exogeneity and linearity. We discussed during chapter 2 that these are hard to satisfy assumptions, and if you want to make them more realistic, you can add more variables. But for now, let's take this example. So here, beta 1 is a causal effect of education, ceteris paribus, on earnings. And the question you can ask yourself is beta 1 different from 0? Is there actually a causal effect of education on earnings? So to answer this question, of course, ideally, you would like to have the data on all Belgians and run this regression, but you don't have that in practice. So you collect a subsample of, say, 1,000 Belgians. You run the OLS estimator. You get some estimator beta 1 hat, but of course in practice beta 1 hat is not equal to beta 1. So it's not equal to beta 1. Beta 1 will be what you will get if you run the OLS estimator on all the Belgian population, but since you only have a subsample, then beta 1 hat is not equal to beta 1. And the natural question is, say you find beta 1 hat is equal to 0.2, can you conclude from that that the true beta 1 is not 0 or not? And to evaluate this, you need to evaluate how much uncertainty or randomness is introduced by the fact that you have a sample of 1,000 Belgians rather than all the population. So to formalize these questions, people do hypothesis testing. So essentially, they are trying to test a null hypothesis, here beta 1 is equal to 0, versus an alternative hypothesis, beta 1 is non-zero. And how do we do that? Essentially, we work like in the justice system and the presumption of innocence. So we start from the assumption that beta 1 is equal to 0. So we start from the null hypothesis. Then we look at what should be under this null hypothesis the distribution of the facts that we should observe. So in the presumption of innocence, if your null hypothesis is person A did not kill person B, then the distribution of the fact is that if this is true, it's very likely that you would have observed person A at work on the day of the murder, and it's very unlikely that you would have observed person A close to the murder place on the day of the murder. In the statistical example, to do that, you use actually that OLS is asymptotically normal. So you know that the OLS estimator will have this asymptotic distribution. So what does that mean? Essentially, it means that there are many different subsamples of 1,000 Belgians on which you can compute the OLS estimator. If you look at the distribution of the OLS estimator over all these samples, it looks normal. But here the catch is, it's normal with respect to the true beta. The true beta usually you don't know, but if you start by saying, I assume that beta is equal to 0, then I know and I can use that. So I know that my beta hat should follow such a normal distribution. no, if the beta hat I have in my sample is very unlikely under such a distribution, I'm gonna reject H0, because I'm gonna say what I observe in my sample is very unlikely to happen if the true beta was 0. If it's very likely to have been generated by a normal distribution, I don't reject. So that's essentially, so this is a distribution of beta hat that you should observe. Essentially, if the true beta was equal to 0, if in your sample you get a beta hat which is on the tails, then it's very unlikely that the true beta was equal to 0, right? Because if the true beta were equal to 0, this should be the distribution of the beta hat, so it should be very unlikely that you are on the tails. If in your sample the beta hat is in this area, in the middle, then it's much more likely that it has been generated by this distribution, so we don't have any evidence to reject. And this is how the test work. So what you will notice here is that the main ingredient of the test here is this asymptotic normality. It's the fact that you know the asymptotic distribution of OLS when the null hypothesis is when you assume the null hypothesis. The issue with lasso is that this is not the case. Lasso is not asymptotically normal, and that's what we saw last time. But first, is this clear for everyone? Is there any question on this? No? Okay. So with lasso, the issue, as I said, is that it's not asymptotically normal, while OLS is. And that's because these L1 penalties, these penalties that we add with the lasso, introduces bias. You will notice that if you look at this formula, that tells you that the mean of beta hat is the same as the mean of beta, right? Because when you have beta hat minus beta, it's a normal distribution, so it means 0, so there is no bias. That's what we know, and that's what we discuss in chapter 2. OLS in general has no bias. Lasso has bias, and we saw that we introduce bias to control the variance. That's what we saw in chapter 2. And that's the problem. For this reason, it's not asymptotically normal, because it has bias. So we need to use different methods that use lasso but adapt it in a way. We saw two of them, double selection and double machine learning, and these methods, they yield in the end, in their last step, an estimator which is asymptotically normal, so for which we can do the same kind of testing as OLS. So this is a model. So you have yi is equal to alpha di, where di is a variable of interest, so say education here. Xi is a lot of controls. So of course this is the lasso case. So you are in the case where you are going to have many controls, and you're going to want to put all these controls to make exogeneity more likely and relax linearity. And you want to test alpha is equal to 0. Another example that we had was a gender wage gap. You want to isolate the effect of gender on wages once you control for a lot of characteristics, because your goal is really to isolate the effect of discrimination. And so here you want to put a lot of controls. So yi is the log of hourly wage, di is gender, and the controls can be occupation, if you work full-time, age, ethnicity, marital status, experience and region, and these kind of things. So that's typically an example. If you really want to isolate the effect of gender discrimination, you want to put as many controls as you want, because you want to isolate the effect of being female or male with respect once you fix all other characteristics. So you want to evaluate exactly what is the effect when two people have the same characteristic except their gender. So that's another example that we saw. So as I said, one naive approach, but that doesn't work, is to use lasso or post-lasso. So lasso is not asymptotically normal. There is another thing which is close to lasso, which is called post-lasso, which is also not asymptotically normal, but the idea of it is you run this lasso estimator. Then this lasso estimator, if you remember, typically it's going to have many zeros. The lasso imposes sparsity, so it's going to have many zeros. That's what we saw also in the first lab session. And then you can say, okay, I'm just going to pick all the variables which have non-zero coefficient for the lasso. And once I've done that, I just run an OLS on these variables. So naively, you could think this works because I have an OLS at the end. So an OLS is asymptotically normal. But this doesn't work. You can see that in simulation. And essentially, that's because what happens here in that case is that the lasso in the first step only selects the variable in X if they are very correlated with y once you control for d. But if you have a variable which is very correlated with di, it's not going to help you predict y. So the lasso is not going to select it, but still it can create a lot of omitted variable bias. So essentially what's happening here is that this lasso step is not selecting variables which are very correlated with di, and that's why it doesn't work. So this just one point, this post lasso can be interesting sometimes still, because often it has better prediction abilities than the original lasso. But that's when you care about prediction, not when you care about causality, so it can be interesting. Okay, is this clear for everyone why this post lasso doesn't work? Okay, very good. So one solution is double selection. So the idea of double selection is you're gonna run two lasso regression. The first one is the one of di on xi, and the second one is the one of yi on xi. At each of this regression, you're gonna get variables in xi with a non-zero coefficient. You select those variables, and then in the last step, you run an OLS of yi on di using as control all the covariates selected in either of the first two steps. And what happens here with this double selection is that, well, first it works at the right-hand side graph, but the second one is like the first regression essentially, it's selecting every variable in X that are very correlated with D, okay, because you regress D on X. The second regression, the second lasso regression selects all variables in X that are very correlated with YI. So essentially, if you take these two lasso regression, the union of variables selected at either of the regression contains all the variables which are either very correlated with yi or very correlated with di. So the only variables that you might miss are just variables which are not very correlated with di and not very correlated with yi. But what we know is that these variables cannot create omitted variable bias or any substantial omitted variable bias. So in that way, we protect ourselves. With the post-lasso, the issue is that we could get variables which are not very correlated with yi, but still very correlated with di. Here it cannot happen because of the first step that we miss. So this is how you run it, but this you will see next week in the lab session, and this is what you find. So around 28% gender wage gap, which is huge. So that this is US data from 2012. Is what double selection does clear, or is there any question? Do you understand this intuition of why you need to run these two regressions? So really the main conceptual point is to first understand from what omitted variable bias comes, and it's really to have omitted variable bias, you need these two conditions. A variable that you omit will create omitted variable bias if first it has an effect on y, meaning like it's correlated with y, and second, it's correlated with di. And so you protect yourself from that by running these first two regression and selecting. Then you have another approach, which, as I said last time, is less intuitive, but is also interesting because its construction generalizes, and we will see that it generalizes to nonlinear model in part 3 of the course, and it's called double machine learning. And the idea is as follows. We use this theorem, one of the most fundamental theorems of econometrics, called the Frisch-Wöhl-Lowell theorem. And the Frisch-Wöhl-Lowell theorem actually tells you that alpha is the coefficient of the linear regression of EI on UI. Here, EI is the part of YI which is not linearly explained by X. And UI is a part of DI which is not linearly explained by X. Essentially, what this theorem is telling you is that you can either control for X in this big regression, or you can just control in two separate regressions and then run an OLS. And this is really a geometric result. Like you can show it, this always works. That's because of the structure of linear regression. But this gives us a natural approach, which is to say, okay, I'm going to estimate EI by a lasso regression of YI on XI and take the residual. I'm going to estimate UI by a lasso regression of DI on XI and take the residual. And then I can finish by an OLS alpha hat, which is a residual which is the OLS estimator of the linear regression of EI hat on UI hat. So you see there are links with double selection because we run the same lasso regression, but rather than using the selected controls, we use the residuals in the last step of it. And so I didn't. So here is is some idea of an intuition which is quite technical. So I will not discuss it again today. But what's really important is that you remember that you have to run these first two lasso regression and then combine them in the last step. And then in this last step, you can just use the standard test of OLS on the last step, and that works. That's the same for double selection. The last step is an OLS, and you can use the standard OLS routine, like the way you compute the p-value, the standard errors, is valid in that case, which is not the case for post-lasso for the last step of post-lasso. Okay, and this is how you run it. So it's also the functional RSO effect, but you change the method. But again, you will see that at the next lab session. And so if you use it on the gender wage gap example, you get almost the same result. So as I said, double selection and double ML, they give you results which are asymptotically equivalent. When n is large enough, the results converge to each other. Okay, so there is no particular reason to prefer one or the other. It's just that they have different interpretation or intuitions. But there is no particular reason. And at the exam, if I don't specify which one you should do, you can do any of them, and that's fine. Sometimes I will specify or ask you to do both, but you can do any of them. Okay, is the intuition with, well, the intuition is complicated, but do you understand what's happening with double ML and what you are supposed to do? Or is there any question on this? Okay. So now we can discuss instrumental variable models. We started last time, but I'm going to slow down again and restart from there. So up to now, we have discussed cases where we assume that if we put enough controls in X, then the linear model we estimate is actually the causal model. And we have some good reasons to do so. We discussed in chapter 2 why adding controls makes both the exogeneity and the linearity assumptions more realistic. But what if it's not enough? It may not fully be enough. So this is one example. So say yi is earnings again, di is education, xi is experience, and epsilon I is ability, some kind of intrinsic ability. You want to know what is the effect of education on earnings. You might put as many controls as you want in X. You will probably never be able to fully control for ability. Okay, of course, the one issue here is you can control for many characteristics. If conditional on these controls, so let's say you take people with the same ethnicity, the same age, that were born in the same US state, and that have same parents' education, it might still be likely that the people who have more education than the people who have less education in this group have different intrinsic abilities. And then if you run the regression, you're going to identify a mix of the effect of education and the effect of these different intrinsic abilities. So what I'm trying to tell you here is that often you could argue that whatever the control you put in your regression, it will not fully be enough to justify the exogeneity assumption. You hope that the exogeneity assumption is more likely to hold or hold in good approximation when you put a lot of control, but it may not be enough. Is that clear for everyone? Do you see why if epsilon I is some kind of intrinsic ability, I can add more control, I can add IQ, I can add parental education, I can add many things, but I will never fully capture it. So the idea of instrumental variables is to somehow overcome this problem. And so an instrumental variable is a solution to this endogeneity problem. So the endogeneity is a case where exogeneity doesn't hold. And there are three conditions, but first I want to discuss one example of instrumental variable in this set. So a very famous example is college proximity at age 14. So say you observe this variable in your data set. So you observe if people at age 14 were close to a college or not. Now what you could do is to say, once I've fixed the value of my control, so I've taken, for instance, people with the same level of experience, then I make two groups. One group is the people who, among these people with the same level of experience, grew up close to a college, and the other group is the people who did not grow up close to a college. Now, normally, these two groups, they will have different average level of education, right? Because it's more likely that if you grow up close to a college, that you go to college than if you grow up far away, because it's much less costly to go to college if you can stay at your parents. So you could say, I look at these two groups, people with the same level of experience, but some have grew up close to a college and the other one did not grow up close to a college. They will have different level of education and they will also have different level of earnings. Then what I can do, and that's the idea of an instrumental variable, is to say, okay, I will look at the different level of earnings that they have, and I'm going to interpret that as a different level, as the effect, the causal effect of the difference in education between the two groups. And this will be a valid interpretation under the three IV assumption. So the first one is exogeneity. So you need that college proximity itself is not correlated with ability. If the people who grow up closer to a college are more able on average than people who do not grow up close to a college, when you compare the two groups, then you're going to get a mix of the effect of education and this difference of ability. So you need to avoid this, and you need to rule out that ability is correlated with college proximity. The second condition is relevance. I said you must have that the level of education between the people who grow up close to a college and the people who did not grow up close to a college are different. Right? Because if they have the same level of education, you cannot use that to identify the causal effect of education, right? Because when you compare the two groups, they have the same education, there is no difference. You cannot identify any effect of education. And then you have exclusion. Exclusion means that the effect of the IV, so IV means instrumental variable, only goes through the DI, the treatment variable, which is education. If growing up close to a college has an effect of your wage, on your wage that doesn't go through education, say you go up close to a college, so colleges often are in, at least in Europe, are in city centers, so you have a better network to find a job, then you run into problems, because when you compare the groups of people who grew up close to a college and the group of people who grew up far away from a college, you're going to identify the mix of two effects. One is the effect of education, but and the other one is just because you grow up close to a college, you have a better network, for instance. Okay, so you need to rule out that this college proximity has any effect on your wage except through the education. So if you want to think, really, if you want to think about these three conditions, do it the way, I think the best way is the way I was trying to present it to you, is just think about when can you interpret the difference in wages between the group of people who grew up close to a college and the group of people who did not grow up close to a college to a causal effect of education. And to interpret it, you need three things: exogeneity, relevance, and exclusion. Okay? Because you need to really be able to say the difference between the wages of these two groups can only be due to their different level of education. And these three conditions guarantee it. I mean, the second condition guarantees that there is a difference of education, and the first and the third guarantee that the difference in wages can only be due to this difference in education. Yes, go ahead.
What if they have a difference in their network, but because of education?
Then I would say, then it's a question of exactly what you want to measure, but then I would say that's still the causal effect of education, so that's fine, right? Like, you might want to say, I want to, it depends what you want to measure, because you might say, I just want to single out the effect of education on skills, not on networking, then you will run into a problem. But if you say, I want the full effect of education, then you're fine. But a very good question. Okay, is that clear for everyone, or is there any of these conditions that is not clear? So this is a very standard technique in economics, but also in like medicine nowadays to estimate causal effects. So one thing I also want to add is that, like, for all of these, in most cases, for these instrumental variables, you can always discuss if these three conditions hold. Okay, like there is a lot of debate. People do not, for college proximity, for instance, some people believe it holds, some other people do not believe it holds, because you could say, okay, when you grow up close to a college, indeed, like your parents are gonna have a better network, so exclusion is not gonna hold. Or you could also say that people select on some kind of ability to have their children close to a college or this kind of thing. So there are many ways, but what's important, I think, is to understand them and to be able to discuss them in a critical manner. So at the exam, sometimes I ask questions about, do you think that this is a good instrumental variable? There is no right answer. You can disagree or you can agree, but what is important is that you're able to think about this, to understand what these three assumptions mean in the particular example of the exam, and to give arguments why you believe they can hold or you don't believe they can hold. Is this clear for everyone? Okay. So when you have a low-dimensional model, so everything is low-dimensional, you're not in a high-dimensional data case, then there is a standard method to estimate this model using the IVZI, and it's called two-stage least squares or 2SLS, and essentially this is running two OLS regressions. So first, you run the OLS regression of DI on ZI on XI, and then you obtain fitted values. So fitted values are just like the predictions from OLS for DIs that are DI hat. And then you run OLS of YI on DI hat on XI. And then the coefficient on DI hat in step 2 is a 2SLS estimator of the causal effect. So this is doing the kind of comparison I was talking to you about, right? Because in the first step, essentially, here you're saying, I fix XI, so I fix my control, I take people from the same level of experience, and then I look at the effect of ZI on education. So that's comparing the level of education of people who grew up close to a college to people who did not grow up close to a college. That's what the first step is doing. What the second step is doing is that once I've done that, I have to look to compare that to the difference in wages between the two groups. And that's what the second step is doing. So the second step is just saying, I take the effect on the variation of education induced by the variation in ZI on my YI, on my wages. Is this clear for everyone? And can you somehow link it to what's happening, like with college proximity and these two groups? If you have any question, don't hesitate. Okay. So now, let's see what happens when you move to an high-dimensional dataset. There are different cases. First, there is a low-dimensional IV case, and then there is a high-dimensional IV case. The first thing, for the first case, what you need to think about is, even in an IV regression, so something like that where I have the instrument ZI, I might want to put a lot of controls. Because the more controls I put, the more I'm making the exogeneity assumption likely in this setting, so I might still want to put a lot of controls. And also, the more I'm still relaxing the linearity. Okay, there is still the linearity here. I still need to interpret this as a causal model, so I still have the linearity. I don't assume exogeneity of DI anymore. I assume the one of ZI. But as we discussed in chapter 2, to make this new exogeneity condition and the linearity more likely, you might still want to put many controls. And once you put many controls, then this 2SLS method doesn't work anymore. It's exactly like OLS. So you need to use something based on lasso to do inference in that case. So how can we do inference in a setting where the IV is low dimensional? So there is 1, 2, or like a few IVs, but you still have high dimensional controls. So you have many controls, okay? So that will be the case in this regression. That will be the case where, say, I'm gonna put many other controls than experience. I'm gonna put parental education, ethnicity, age, IQ, and interaction of them. Think of this as this. Then the first thing I can do is somehow adapt double selection, but to IV estimation. And to do that, well, I'm gonna run the same lasso regression as before, like the one of DI on XI, the one of YI on XI, but also another one, which is the one of ZI on XI. Then I'm gonna take the controls that are selected by any of the three lasso regression, and I'm gonna run a 2SLS of YI on DI using ZI at IV and with controls selected by either of the three above lasso regression. So if you remember, for the standard double selection where you don't have an IV, you do step 2 and step 3, and in step 4 you do OLS instead of 2SLS. Here the idea is very similar, except that in a sense the omitted variable bias becomes more complicated, because you also want to avoid omitted variable bias to select variables that are very correlated with the IV. And to do that, you need to run regression 1. Is this somewhat clear for everyone? And what is the difference? Yes.
You still use all the variation in ZY in the fourth, but you don't use like fitted values of the first lasso?
Well, you will use fitted values, but the fitted values are true to SLS. Okay. You see what I mean? So then this fourth step corresponds to the 2 SLS. So in this first step, you're gonna first run an OLS of the linear regression of DI on XI on ZI on XI, where XI in that case are the controls selected at any of the first 3 steps. And then you have fitted values there. Does that answer your question?
I think so, but you're not taking any variation out of ZY.
No, not at all. Yeah. So you still use the I as before. This is just a mechanism to select the controls. So if you remember double selection in the linear model, essentially the last step is OLS, and we do the first 2 steps to select the right controls. Here, the last step is 2SLS, like you will do in a low-dimensional setting, but we do these first 3 steps to select the right controls. And the intuition is very similar. It's about omitted variable bias. But in the case of IV regressions, there is a third condition for a variable to create omitted variable bias, and this third condition is this variable must be correlated with the I. And to protect ourselves from that, we run the first lasso regression here. Okay, so now I'm gonna give you an example. So this is an example from this paper by Acemoglu, Johnson, and Robinson. So Acemoglu got a Nobel Prize very recently for this paper. I think it's a terrible paper, but it's a very famous paper, and I think the IV is terrible personally, but I think it's good to see that to just have a look at this kind of important paper, and then we can also discuss the IV and see how you apply it to this setting. So so Acemoglu is an economist, and his main thesis is that what explains causally economic growth is institutions. You need to have strong institutions, the rule of law, universities, a state, judges, all of this. And once you have strong institutions, that's how you get economic growth in the long run. Now, if you want to demonstrate that from data, it's a bit complex because there can be reverse causality. Some people will say that's because you have a lot of economic growth that you have the money to set up institutions, or it could be the other way around. You have institution, and that causes economic growth. What you observe in the data is that both are correlated. Like countries with the most institutions typically over the history had the best economic growth, but this is not. It's a correlation, not a causation. So to kind of uncover a causation, he considered 64 countries, and all these countries are former colonies. And he wants to run this regression. So he wants to take the log of the GDP per capita of these countries and regress it on a measure of protection from expropriation. So this is just for each of these countries, you have a measure of property rights, how strong property rights are in these countries. In some countries, the state can easily expropriate you. In some other countries like Belgium or the United States, it's much harder. So he has a measure on that, and then he has some control variable, and essentially the control variable, they are just there to control for climate. So these are many non-linear terms in latitude. He wants to run this regression, but now he says, okay, I believe protection from expropriation is endogenous, because it might be that because you have a better GDP, you can protect more people from expropriation, or the contrary. And he uses an IV for it, which is called the settler mortality at the time of initial colonization. So the idea here, and I think again it's a very bad IV, but that's the argument of Acemoglu, is to say, so these are all these countries are former colonies, and when they were first settled, when you had first colonization, the colonizers had very different mortality rates. Sometimes that's because you are in parts of the world where Europeans were very vulnerable to diseases or these kind of things, or the climate was very bad. And his argument is to say, okay, when you have a very high mortality, you are less likely to set up institutions, so to set up low protection from expropriation, than if you have a very low mortality. Sorry, the contrary. When you have a very high mortality, yes, you are less likely to set up institutions than when you have a low mortality, right? Because when you have a low mortality, you think you're going to be there on the long term, so you want to take the time to set up institutions. When you have a high mortality, you are going to be there. You think you are not going to be there for the long term, so you don't take the time to set up a state or institution. That's his argument. I don't think it's very convincing, but that's the main argument that he is doing there. And it's as I said, it's controlling for what people do is control for latitude because the climate might influence both economic development and mortality. So this is the regression. So here is a table from this paper. Well, the reference is at the end of the slide. And this paper is revisiting this paper of Acemoglu using Lasso to estimate the IV model. So in the first column here, you see what happens if you just run standard 2SLS in this regression, where in Xi you just have latitude. You don't have any nonlinear term in latitude, you just have latitude. So what do you find? So you have the first stage and the second stage of 2SLS, but essentially you find a coefficient of 0.96 and a standard error of 0.21. Then you have a second column called all controls. So this is a case where you introduce many nonlinear terms like polynomials, like squares in latitude as controls. In total, you have 16 controls. So 16 controls for 64 observations. And then you just run still 2SLS. And what happens, the coefficient barely changes, but you see that the standard error explodes, which is what we expect because we said like with OLS, and the same happens with 2SLS. When you run OLS in a high-dimensional dataset, so when you have many controls, then the variance explodes. That's what we saw in chapter 2, and that's what you see here. Now what they do here is, okay, they take the same case with 16 control, but in the last column, they do the double selection that I showed you. And then what you see is that you find a coefficient which is markedly lower, 0.77, and more interestingly, the variance, I mean the standard error here, is much smaller. What is in parentheses is a standard error, and the standard error is much smaller when you do double selection. And that's what we saw. You remember, Lasso, in high-dimensional datasets, Lasso controls the variance in a way that OLS cannot. And here, double selection is controlling the variance in a way that 2SLS cannot. So that's what you see in this application. We can debate if this is a good IV or a good application. But what you see markedly is that using this double selection at least reduces by a lot the variance and can change the result. And that's important to keep in mind. Is this clear for everyone? Okay. So as for double selection, there is also an adaptation of double LML to this setting. And essentially, the adaptation of double ML also uses the Frisch-Wohlovel theorem. And the Frisch-Wohlovel theorem tells you that alpha is the coefficient of the 2SLS regression of EI on UI using VI as an instrument. Here, EI is a part of YI which is not linearly explained by X. UI is a part of DI which is not linearly explained by X. And ZI is a part of VI is a part of ZI which is not linearly explained by X. So that's extremely similar as before, except that we move from OLS to 2SLS. And then what can we do? Exactly as double ML for the standard linear regression without IV, we are going to estimate by different lasso regression this EI, UI, and VI, and then we are going to run 2SLS. So that's again like an adaptation of the double ML of before. So first, I estimate EI by the lasso regression of YI on XI, and I can also use post-lasso, not only lasso, both are fine. Here I do the same for UI, for VI, and then I run a 2SLS of EI hat on UI hat using VI hat as an instrument. And what's important is that you can use, on this last regression, you can use the standard errors of the classical 2SLS, like that are given by your software, and this works. You can show it in theory. Is this clear to everyone, or do you have any question? Do you understand? Yes?
Could you maybe, which equations are estimated in the last 2LS?
Which equation? Okay. So essentially what you can show is that under the assumption of the model, you have this. So if you look at the linear regression of EI on UI, then its error term isn't correlated with EI. And this is what you are estimating in the last step. So you're estimating this by 2SLS using ZI as the instrument. Sorry, put ZI, I meant VI. So you can show that. That's exactly what is estimated by the last 2SLS, okay? Is that okay? Yeah.
VI is the estimate again.
Well, still in practice, VI is VI at, yeah. But in theory, there is some VI, but we estimate it. We don't know it. Is that clear for everyone? That so you can actually show, because you can actually show this that this holds using these different equations, but it takes some computation. And the Frisch-Wohllowel theorem. So the proof is not so simple, but essentially this comes from the Frisch-Wohllowel theorem. The Frisch-Wohllowel theorem tells you exactly this. Essentially. Are there other questions on this? Don't hesitate to ask. Okay, so what I propose is that we have a break now until 10:05, and at 10:05 we start again. Okay, let's start again. Is there any question about what we saw before the break? Or is everything clear? Okay. So now we are gonna talk about another example, but in this new example, we will also be in the case where you have many instruments. So far we were saying there are few instruments and many controls, but now we can see the case where there are many instruments, and I'm gonna give you an example of application. So one example is what we call eminent domain. So we were talking about expropriation before. So eminent domain, it's an American term, and it's a set of laws that allow US states to expropriate people. So let's say you want to build a new road, you might have to expropriate some people. This is allowed by eminent domain. It's also called taking laws. You want to build a train line, you also might have to do that. You want to build a mall. Sometimes people get expropriated for building a mall. And so every state, US states, has kind of different taking laws or eminent domain procedures. And they are frequently challenged in court. So you can challenge, like, if the state wants to expropriate you, you can always challenge that in court, and there are lots of challenges. And there is a lot of debate on what is the effect of this eminent domain on some economic variables. One question is on house prices. So you could say that if there is eminent domain, a strong eminent domain law in a state, the house prices are going to go down, because you know that you might be expropriated by the state. Of course, the state is going to compensate you, but you might have to move somewhere else. On the other hand, states which have strong eminent domain can have better facilities, because then they can expropriate when they need, when they want to construct a road, to construct a train line. So the effect is ambiguous, and that's the same with economic development, right? Like for economic development, trust of people in institutions is important, as we discussed before. So the fact that you cannot be expropriated can be good, but at the other hand, if you can never expropriate anybody, there are lots of projects that will not happen, and having new roads, for instance, is important for economic development. So here there is a question, it's not really clear, it's ambiguous, like, are such taking laws important, are they having a positive or a negative effect on economic development? So as I said, the law are often challenged in court. One issue that you might have here is, okay, let's say I want to know what is the effect of such law on economic development. I could say, essentially, I regress economic developments of US states on how strong their taking laws are. The issue with that is, it turns out that for instance, democratic states have stronger taking laws, but they are also richer, like the states that vote very much for the Democrats. And this might be because of their ideology, that they have stronger taking laws, but their ideology can also explain their economic development or their house prices. So in a way, this is fully endogenous, right? Like, it might be that on one way, states which are more developed are more likely to implement taking laws, or it might be that taking laws make these states more developed. It's never fully clear, because the process of forming democratically these taking laws is really intertwined with economic developments. What's interesting is, you can use the court challenges to these laws to construct some IVs. Because in the US, when you challenge a decision from the state, or you challenge any decision, the judge to which you are assigned is randomly assigned. So the judge that you get might be more against taking laws or more in favor of taking laws. And in a way, this creates variation on how much the taking laws are applied in practice, but this variation is what we call exogenous. So what I want to say here is, every year in every state there are a few eminent domain court challenges. If in a given year these eminent domain court challenges are given to judges who don't like taking laws, then taking laws in that year are going down, like their strength and their effect. If randomly they are given to judges that like taking laws, then the strength of taking laws is going up. Here the idea is to say, my instruments, my IVs, are going to be demographic characteristic of judges. So, for instance, it could be that older judges are more against taking laws, younger judges are more against taking laws, male judges are more against taking laws, or one or the other. If you got your law degree in a public school, you might be more against taking laws than if you get it in a private school, and it goes on. So the idea here is just to say judges are randomly assigned, so their demographic characteristics are exogenous, and we use that as an instrument because this is going to create some variation on how the taking laws are applied in a state, and we can use this variation to estimate the effect of taking laws on economic development. So this you will discuss it in the next section. The section is application, but this is just to give you an example. Here, what you need to understand mostly is that you have many instruments, because any demographic characteristic of the judge can be used as an instrument. And you have many demographics. So you have ethnicity, age, gender, where they got their degree, and you can interact all of these things, okay, and put non-linear terms, so you have many IVs. Yes?
Is it not difficult to satisfy the exclusion restriction when it comes to these things?
Why?
Or is it really
Because
completely random assignment?
here, so the assignment is fully random. That's the thing. So it is fully, like in the US, the assignment is fully random. It's really a lottery. And then essentially the judge that you get is in theory only going to affect the strength to which taking laws are applied through their own demographic and their decision, but only through this decision. Yes?
For example, if you take age, you just have age is also correlated with this point in time you have the case. When it comes to judges, for example, right? Then you might have an issue, no?
So you have, I mean, what matters is not really of course the average age is gonna be different from year to year, but what matters is the variation between cases of age, and this is still gonna be random. So I think this is fine. But so in that case, I mean, it's I think these are are kind of good instruments. Yeah. So I think these are some more good instruments in that sense. The issue is the relevance condition might be very weak. So this may not have so much effect on taking laws, and so this relevance condition might not hold so well. But for the exogeneity and exclusion, I think in general these are quite good instruments. So exogeneity and exclusion are somehow guaranteed by the full randomness of the process here. But now, is this really relevant? Do this cause a lot of variation in the level of taking laws? This is much more debatable, I think. But this is just one example. So now you have two cases. One case is you have many instruments, so the instruments are high dimensional, but you have low dimensional controls. So you put very few controls. So for instance, here in the example of our application, I is a US state. You could put one control is the share of democratic vote at the last election, for instance, something like that. Then it's actually very simple to do inference. Because you remember that when you have two SLS, the first step of two SLS is a prediction step, right? You take the fitted value, the predicted value. And lasso is also a prediction device. So you can actually just replace the first step of two SLS by a lasso regression, use it as a prediction device, and then keep the second step the same. So you're just using the prediction from the lasso, and that works. But that's really because the high dimensionality here is in the IVs, and you use the IV for prediction only into SLS, and it's not in the control, the high dimensionality. So it's a very simple adaptation where you just replace the first step of two SLS by a lasso, because the first step is a prediction, and you have to do a prediction now with many instruments. So you regress DI on ZI on XI, and to do this prediction, you can just use lasso. That clear for everyone? So this is even more simple. This very particular case where the controls are low dimensional is actually way more simple than all the cases where the controls are high dimensional. And that's because 2SLS, the first step, here the issue will only be the first step of 2SLS. That's where the many instruments appear. And this is a prediction step, so we can use lasso. Okay. So now let's discuss the case where you have high dimensional controls. So now on top of that, so you have many instruments, but also you have high dimensional control. So you put many more variables in the control. So in the example of eminent domain, you're going to put democratic vote, but also some demographic variables about the state, like how many people are over 60, how many people are below 20, what is the climate, what is the level of economic development, and these kind of things. Okay, so you could also put a lot of controls, and that's what happens here. So if you remember 2SLS, so 2SLS is two OLS steps. The first one is a prediction step, right? And then the second one is just a standard OLS. Now you have high dimensional controls. So since the first step is a prediction step, you can just do it, as we said just before, you can just do it with lasso. You can just run a standard lasso for the first step, exactly like before. But now the difference with before is that in the second step, you have high dimensional controls, while on the previous slide, you did not have this. So the second step, you can't do just by OLS anymore. And the second step is not only about prediction, it's about really estimating the causal effect. So the second step, you need to replace by double ML. So the second OLS step of 2SLS, you have to replace it by a double ML, or you could also do a double selection, by the way. And so this is what happens here. So in the first step, you obtain the fitted value by a lasso regression of DI on ZI on XI. And then for the second step, so the second step used to be just OLS of YI on DI hat on XI, but when you have high dimensional controls, you can't do that anymore, right? So then you do double ML, you replace the second step by double ML. So first, I do the lasso regression of YI on XI, I get some EI hat. Second, I do the lasso regression of DI hat on XI, I get some residual RI hat, and then I do the OLS of EI hat on RI hat. Okay? So essentially, the second step OLS regression, you just replace it with double ML. Are there some questions on this? Yes? Yes. So penalizing is just, okay, that's a good question. Here, since you remember, like in the lasso, you have this term where you add a penalty for the beta k. And when you mean non-penalizing, it's just in this penalty term, you're not going to put the coefficients of the x variable, but only the coefficient of the z variable. And that's because you don't need to select at all the x variable because they are low dimensional. So you don't need to penalize. This fine is fine. It's only the z variable that you need to select. And you saw, so one important point, you should notice it here is, for instance, when you do like the standard post lasso, here you saw, for instance, we did not penalize the alpha. So sometimes we don't penalize all variables. Okay, so you can just do lasso, like the standard lasso is you penalize all variables, you put the sum of the coefficient of all variables, but you might also say there are some variables I don't want to select them, so I don't put them in the penalty. I want to make sure their coefficient is non-zero, so I don't put them in the penalty. Is that clear for everyone? I know there are lots of algorithms but really what's important is mostly to understand like double selection and double ML, and once you've understood that, for the IV these are just variation, and I know there are many, but the intuitions are not really different. It just looks more complex. Okay. So we are done with this chapter. So we saw for the IV different cases, like just low dimensional IV, high dimensional controls, high dimensional IV, low dimensional controls, and then where both are high dimensional, and we are done with that. So next week, there will be a lab session in the computer room of the library. I will not be teaching it. It will be the TA who could not be there for the first lab session. But you're gonna essentially apply all these tools in the lab session of next week. Not yet the part on IV, I think, if I remember. Yes. Yeah.
Last slide. Is there a reason why there's a hat on the last coefficients there at the controls?
So
We're using the residuals.
that's because it's a residual. So this is the lasso estimator. I have an hat here on the coefficient because this is the lasso estimator, and then I take the residual of it. Is that clear? On?
Oh, yeah.
Yeah. Okay. So are there any questions left on this chapter? Okay, otherwise we can start chapter 4 and part 3 of the course. So in the part 2, we only discussed linear models. We were always assuming this assumption of linearity. Of course, we relaxed it sometimes by putting polynomials, transformations, but we were always estimating a linear model. Now in part 3, we are moving to non-linear or non-parametric. I will explain what are non-parametric models. And we are going to discuss how to use machine learning to estimate non-parametric models, so that avoids the linearity assumption. And we are gonna also discuss how to estimate a causal effect in that case. And again, we will have the same contrast between techniques which are for prediction at the beginning, and then we will have to adapt them for causality. But the nice thing with all these non-parametric models is that we can relax this linearity assumption, fully relax it, and this is really a strong advantage. But these are more advanced techniques. So first, I want to discuss what are non-parametric models. So to understand what it is, so suppose you want to predict a variable y given some variable x. Let's take again the example of house prices. I want to predict the price of a housing unit as a function of the number of square meters and when it was built, let's say. One way to do that is to try to find the best linear predictor, so the best fitting line from y to x, and that's exactly what you can do with OLS, and that's what we did in part 2. Now, what you can show is that in theory the best possible predictor is what we call the conditional expectation. So the best prediction here would be and that's a theoretical object, the average value of y for subjects such that x equal x. So if you have a flat with, let's say, 100 square meters built in 1990, then the best prediction of its value is probably the average price of flats which were built the same year and have the same number of square meters. That's logical, right? That's the best prediction you could think of. This prediction is not linear anymore, right? Because for instance, you might think that so if this is number of square meter and this is price, maybe, and that's mostly what you observe, the price of a flat increases but non-linearly with the number of square meters. The price per square meter is lower for big flats than for smaller flats. So ideally, if you want to do your prediction, you would like to know what would be this average price of a flat with exactly the same number of square meters and the same year where it was built as your own flat. Now the difficulty with that is that if you have a sample, typically you will have 0 or very few flats which are exactly built the same year as your flat and have the same number of square meters, right? So in a way, you have some kind of trade-offs. This is the ideal object you would like to estimate. It gives you better predictions, but this is much harder to estimate. The best fitting line is much easier to estimate than this, because this is very hard, as I said, because this is the average value of the price of flats for flats which have a given number of square meters. And in your sample, in your data, you might have very few flats which have exactly 100 square meters or exactly 101, and it goes on. So that's why people sometimes use linear models. So linear models, they look at the best fitting line. This best fitting line is, on average, if you were to know the line, like you're trying to estimate it, but if you were to know it, it would give you worse prediction than if you were to know the conditional expectation. But the best fitting line is easier to estimate than the conditional expectation. So you have trade-offs in a way. And that's why people use linear models, because they are trying to estimate an object which is easier to estimate. Even though this object is less interesting for prediction, it's easier to estimate. Is that somewhat clear for everyone? Are there some questions on this? So the best fitting line essentially is something like, in that case, is like something like that. That gives you worse predictions, but it's going to be much easier to estimate. To estimate this curve, you really need to localize. So you really need to, if I want to know this, I need to look at flats which almost this value of x and take their average. To estimate the line, I can use data from everywhere. So to justify the different approaches, in statistics, as you have seen, we have models. And essentially, in a way, models have different level of flexibility. And the least flexible are parametric models, and the most flexible are non-parametric models. And in the middle, you have what we call semi-parametric model. I will talk about that. But essentially, when you look for the best linear predictor, you're looking for a semi-parametric model. You're trying to estimate a semi-parametric model. So you're trying to estimate a model which is not too flexible. When you're trying to estimate the conditional expectation, this is a non-parametric model. So you're trying to estimate something which is extremely flexible. So first, let's start with parametric models. So a parametric model, it's a model where the distribution of the data only depends on a parameter theta that belongs to RQ, so it's just a real parameter. Okay, that's just a finite number of numbers. So one classical example can be a linear model with Gaussian noise. So you assume that y is equal to x prime beta, and you say plus epsilon, and you say epsilon is independent of x and follows a normal 0 sigma square. Then here you know exactly the distribution of the data. So you know exactly the distribution of y given x, because in that case y given x is just a normal x prime beta sigma square. And so the distribution of y given x is fully determined by beta on sigma square. So it's fully determined by real numbers. Another example is a probit model. So it's a case where y is a binary variable and its value is 1 when x prime beta plus epsilon is positive, where epsilon is independent of x and follows a normal 0, 1. And it's 0 when x prime beta plus epsilon is negative. Okay, and here the same, what determines the distribution of y given x, like for a certain value, for a given value of x, the distribution of y is fully determined by the beta. So it's determined by a real number. And these models, so they are not very flexible, which is a problem. They are very easy to estimate because you just need to estimate a parameter. And you can do that by maximum likelihood. Then you have semi-parametric models. So semi-parametric models, it's the case where the distribution of the data depends partly on real numbers, on a parameter, but also on what we call an infinite dimensional parameter, so a function. I know this is quite theoretical, but just try to bear with me. So one example is a classical linear model. In the classical linear model, you don't assume anything on the distribution of epsilon, except that it's uncorrelated with x. That's what we saw in the previous chapter. Then here the distribution of y given x can be is fully determined by two things. First, the beta parameter. So this is a parametric part of the model. And the distribution of epsilon given x. This is the infinite dimensional part of the model. This is not a real number, this distribution, it's something infinite dimensional. And so what's nice with this type of model, and that's what we saw before, is it remains somewhat flexible. I mean, this is more flexible than the linear model with Gaussian error, because we don't assume that there are Gaussian errors. But it's still simpler to estimate. We saw we can just do that with OLS, and we can form predictions as x prime beta hat, where beta hat is just the OLS estimator. Then you have non-parametric models. So these are models without a parametric part. So these are models where there is no parameter. You're always trying to estimate estimate a function, essentially. And so one example here is just the conditional expectation model. So for any random variable, y, you can always want y is equal to gx plus epsilon, where epsilon is equal where gx is the conditional expectation of y given x, and epsilon is mean 0 conditional on x. Okay, this you can always do, right? Like you can always say my y, it's equal to its conditional expectation given x plus an epsilon, and this epsilon is just y minus the conditional expectation. So here epsilon is just y minus this, And so you see that by construction, the expectation of epsilon given x is just the expectation of y minus the expectation of y given x conditional on x. So this essentially is already conditional on x, so this is fixed. And so you can develop this thing and you get expectation of y given x minus the expectation of y given x, and this is just the expectation of y given x. And here you get to 0. Okay, what I'm just trying to tell you here is for any random variable, you can say that the random variable is the conditional expectation plus an error term. So if you have a flat which has 100 square meter, then its price is going to be equal to the average price of flats which are 100 square meter plus an error term. And this error term will be mean 0 by definition of the average. That's just what we are trying to say here. Is that somewhat clear for everyone? The maths might be advanced, but this is not so important. What's really important is just you realize, okay, I will often write a model like that, and this model just means if I have the price of a flat, and this flat is 100 square meters, and this price is equal to the average price of flats which have 100 square meter plus some error term, and this error term will be mean 0 by definition, right? Because this is just a variation to an average. Are there questions on this? Are there things which are not clear? Okay. Yes.
I don't understand why it has mean 0.
Yes. So if you take an example. So I'm taking. So you're all gonna get a grade at this course. I am looking at your grade, and I'm comparing your grade. I'm comparing the grade of each student to the average. So here the average of the class is the conditional expectation, and the epsilon is just the difference between the grade of a student and the average of the class. Do you agree that by definition of the average, if I take the sum of all these epsilon, then it's going to be 0, right? And that's exactly the same that's happening here. Okay, so that's why essentially you can always write a y like that. You can always write y like that, and your gx will just be the average of y given x. In my example here on the class, there is no x, let's say, but that's okay. So I could also do. You come from different masters, so I could take the class and I could say for a given person, I don't compare its grade to its average. I compare its grade to the average of the people who are in the same master as this person. So my x is like the master, and then I will have the same property, right? That if I take the sum of the differences between the grades and the average in the same master, then I get a 0. Is that clear for everyone? So that is thanks for your question. Very good question. So essentially here what's happening is you have this model, and as I said, the gx is going to be a better prediction than x prime beta. That's something very intuitive, but it's better to predict the price of a flat with the average for people who have the same for flats which are similar than with some kind of linear model that does extrapolation. But it's much harder to estimate gx. Now what's interesting is that when you have big data, meaning you have a very large n, you might have some hope to estimate gx precisely. What I mean by that is if you have many flats in your dataset, then you probably will have enough flats of around 100 square meters to be able to estimate the conditional the average price for flats which have 100 square meters. If you have a very small data set, that will be very hard, right? Because if you have a very small data set, you will probably not have any flat which has 100 square meter or even like 105 in your data set. When you have a very large data set, it's easier. So what I'm also trying to tell you here is when you have a small data set, you need to go through a parametric model because there is really no hope to estimate a very flexible model. When you have a large data set, then you can go to non-parametric models. So just one thing, so you can estimate, and we will discuss this, but you can estimate by machine learning the G, but there is a simpler way to do that, and it's almost what we discussed already in part 2, is to say, to estimate G, I can just say, I'm gonna run an OLS of Y on 1, X, X squared, XP, and these kind of things. I'm gonna put many nonlinear terms in my linear regression. And essentially when you do that, you relax the linearity assumption, that's what we discussed, and you're gonna approximate G very well. You're gonna approximate the nonlinearity very well. And so what you do here is, if you do this kind of regression, it's called series estimation. So you put a series of linear terms and you use that to do some kind, to estimate a non-parametric object. And here I put just standard polynomials, but you can consider other transformation of X. Now here you have a little bit of difficulty, is how do you choose P? How many terms do you put in this regression? Because what we know is, okay, you want to put a very large P. Because the more P is large, the more you relax linearity, the more you're estimating like a flexible function. So the more you approximate G well. But if you put a P which is too large, as we saw in part 2, you have overfitting and OLS fails. So all the discussion is how do you choose P? What we proposed in part 2 essentially is to say we are going to take a very large P, but then we are going to have an overfitting problem, and so we are going to do lasso to solve it and assume sparsity. Right? That's one solution. So one solution is to say I'm going to have a very large P and use lasso, but then you need to assume sparsity, meaning only a few of these polynomials have a non-zero coefficient. So this is the limit of this approach. Another approach is to have a lower P, then you reduce overfitting, but the issue with that is you may not approximate every type of non-linearity in G well. And now there is a third approach, which is not to do this kind of series estimation, is to use some machine learning techniques that we will discuss next time. And the advantage essentially of the machine learning techniques is that implicitly they have a computational way inside to control the level of overfitting. And that's what we saw with the lasso, right? The lasso, when you do cross-validation for lambda, essentially you are controlling the level of overfitting, and the machine learning will do the same in that case. And just one example of series estimation. So this is, here you have a data set of people in the US, and you want to predict wage of people. So this is a wage as a function of their age. And here essentially it's running a linear regression where you have a constant age, age square, age to the power 3, and age to the power 4 as variable. And then you see, of course, that these are the prediction. So this is like, let's say, the x prime beta hat of this linear regression, and you see that you get some nonlinearity. But of course, the amount of nonlinearity is limited because you only have a polynomial of degree 4. So the polynomial of degree 4, for instance, cannot approximate well a polynomial of degree 5, of degree 6, and cannot approximate well every possible G. The more you increase the degree of polynomial, the more you approximate well. But as we said, you have trade-off with that. Okay? Is that somewhat clear, at least this introduction to non-parametric models so far? Okay, so the only thing I want to say, because I think this was short, so maybe there is no need for a summary, is so if you want to learn more about this, you can have a look at this book. This book is on Toledo. It's freely available also through the library, and you can look at chapter 7 here. What we will do next time is that we will discuss, let's say, so in 2 weeks, we will discuss 2 of the leading non-parametric machine learning methods. One is random forest, and the other one is neural networks. So neural networks are the one variation of it are the one behind like large language models, ChatGPT, and these kind of things. But mostly in practice, we will use random forest, which is a bit simpler and works better with economic data. Okay, so and just to summarize what we did today, so we discussed again the IV. We saw somehow how to adapt estimation of IV models to the case with high-dimensional data. And what's important to remember is that when you have low-dimensional data, you estimate IV model by 2SLS. Both steps are OLS, but the first step is really a prediction step, and then the second step is like a more standard OLS. So the first prediction step, when you have high-dimensional data, you don't need to change it essentially. When we have many instruments, you don't need to change the first prediction step, but you need to change the second step and replace it by double ML or double selection. When you have low-dimensional IV and high-dimensional controls, then you need to essentially do a third selection step to make sure everything works well. Then we move to chapter 3 on non-parametric models, and essentially what we discuss is again this idea of overfitting. When you have a small data set, you should not try to estimate a too flexible model, because otherwise you overfit. And in other words, that means the object you're trying to estimate is too hard to estimate for you, given the size of your data set. And in chapter 2 and 3, we were focusing on linear models, which have some kind of limitation for prediction. And now we are going to move to nonlinear models and trying to estimate essentially this object, which is a conditional expectation. And as is quite clear, these nonlinear models, they avoid the linearity assumption. So this is nice. In particular, when you look for prediction, it's nice because this object, as I said, even if it's harder to estimate, it's better at prediction than linear predictions. And for causality, it's also nice because we relax this linearity assumption, and you remember that the model you actually estimate has to be the causal model. And there is no ex ante reason to believe that the causal model is linear, so you want to relax this linearity assumption. Okay, any question? No. So otherwise, so next week, as you said, lab session in the Econ bibliothèque, and then we see each other in 2 weeks.